My name is Svacina, and I'm going to present you a paper on semantic code clone detection for enterprise applications that I wrote with Jonathan Simmons and Tomas Cerny. Enterprise software maintenance and costs is a primary focus of many corporations, as they get a huge revenue from fees for maintenance. And next issue is also the quality assurance from the point of view of creating the software, that the maintenance is very important, so it reduces the time the programmer spent on developing a program, and it has many also implications on readability and so on. The impact of a good code is significant, because when the code is not structured well, there are very often duplicates of code, which we describe as code clones, and it is estimated that it is up to 10. It is from 10% to 23%. So the reducing code clones can have a substantial boost in code quality of a software project. And it is also well known that the bigger project is, the more is the maintenance costs and the more code clones there are. So the code clone detection is very popular problem in software engineering and in computer science, and there are also tools for reducing code complexity within applications. And right now, because software engineering because enterprise projects are taking up, it takes a huge portion of industry, and it is very important to focus on these applications from a semantic point of view, because semantic code clones are the hardest to find and is hardest to tackle. But as I'll show you later, the enterprise applications are the primary focus of semantic code clones. So our approach we used inter-procedure control flow graph model, and used this model of complexity of n to 2. Our hypothesis is that we detect semantic code clones in enterprise applications using semantic meaning of the program. Before I begin with our algorithm, I need to clarify what the program analysis is. It is to get information from code and executions, reason about the code and executions, and determine the program properties. And the program analysis tool ultimately is a software analysis of other software, like compiler. And for our purpose, is very important to take the third property of program analysis, and it is to determine program properties, because we will use the program properties to find those semantic code clones. We can analyze the program statically or dynamically. Statically by analyzing source code, dynamically by analyzing executions. And we can represent a program by a control flow, execution, which is execution order of statements, so like the parse tree or data flow, how the program variable usage pattern is going on, but we will use interprocedural control flow to get information through all procedures in the program. So what a control flow graph is a procedure of a control flow graph of a procedure is a graph. It has nodes and edges. The nodes are statements, and edges is how these statements are going one by one. And when we talk about interprocedural control flow graph, it is a collection of control flow graphs that are connected together. Each procedure is connected with another procedure and another procedure, and so on. But in my presentation, I will be using the CFG and ICFG interchangeably. So this is an example of CGF or ICGF. This is a very popular pattern it's in Java, and it is a very popular pattern for in a enterprise frameworks to handle a particular procedure. This procedure takes a POS, point of sale object, and persists this new object into a database. Commonly, we use 3 layers: a controller, service, and a repository. And these are separate functions. Each function has a certain meaning. For instance, the controller accepts the value, service preprocesses it, and repository presses the object into database. So 3 calls, and we can one by one they are going, but we can derive from them properties. The controller gives us properties of a type, argument, return, type, and security, and this same can be applied on service as well. We have here just argument and return type, and repository as well, the return type and argument, and also a database type operation. As we can see, properties can define a control flow graph. So we take the source code, we make a graph transformation into control flow graphs, as I showed you earlier. We make a graph quantification, which is that we observe its properties, we parse the properties of every CFG, and then we input these CFGs with properties into the similarity function, and the similarity function gives us clone paths of how close individual CFGs are, and then we classify all those clones by a measure, and hence the classified clones. So we take a source code on the left, we produce the graph on the right, we produce properties on the right, and then we take these CFGs and input them into the similarity function that gives us the similarity each with each. So each CFG with each CFG gives us a similarity. Here is a table that demonstrates how it looks. There are properties of each control flow graph. Then the similarity function provides us simply with a global similarity. That means that we compare everything together, and the local means that we compare the controller functions, repositories, and calls to another function separately, one with each other. So in our case study, we took an enterprise application. We derived 20 CFGs, which resulted into a total combination of 190, and we found altogether 6 clones that we categorized in these categories, A, B, C. A is the clone that is the most similar, it's above 90%, B above 80, and so on. So in the future work, we can enhance this situation by a better code preprocessing, which means that we can focus only on a part of code base that is worth to analyze the data, not some configurations and so on. And of course, more metrics to report, more metrics about control flow graphs and so on. So thank you very much for attention. Goodbye.